thank you very much for coming today. So we have a very nice talk from Thordis Thorarinsdottir, who's working in Oslo. And Thordis, the floor is yours.
Thank you very much. Good morning, everyone. Thank you for coming. So I'm going to talk about how to do predictive evaluation with scoring rules and scoring functions. I'm going to have some focus on extremes because we have some interesting sort of problems with extremes, most of which is that we usually don't have a lot of data because we're looking at rare events. There is also in the workshop next week, there is quite a number of talks that are related to this. So what I did here to get sort of put together kind of the first half of the talk is a very broad introduction. So very basic introduction. There isn't a lot of us. I'm wondering if you do have any questions at some point, if you just want to raise your hand and we can take the question then and there. I don't know if we have constraints, or we can also take questions at the end. So we can just, if there's something you're like, wait a minute, help, then just raise your hand and we can talk about it. But first, before we talk about mathematically how to do forecast evaluation, we need to talk a little bit about what does it actually mean for a forecast to be good. And here's what I think is a very nice quote from Alan Murphy. So Alan Murphy was a meteorologist. And for very many decades, he worked on sort of how to say what is a good weather forecast. And so he published a lot of papers, and there's a lot of kind of the sort of the way we think about how to evaluate forecasts. A lot of that comes from Alan Murphy and his colleague Robert Winkler. And so what he says here is that forecasts possess no intrinsic value. They acquire value through their ability to influence the decisions made by users of the forecast. Right? And I actually really like this quote because we always have to think about sort of when we're predicting something, is this a useful prediction? Right? And so we have to kind of connect our models, our forecasts, a little bit to how they're actually used after we have done our modeling. And then in the same paper or an essay, Murphy goes on and says, this is what I think we need in order to say whether a probabilistic forecast is good. So now we moved over to thinking about forecasts where I issue a probability distribution as a forecast for a real valued outcome. And he says there should be consistency between the forecaster's judgment and the forecast, correspondence between the forecast and the observation, and the forecast should be informative for the user. Right? So the one in the middle, correspondence between the forecast and the observation, right? That is what we usually try to evaluate when we're doing forecast evaluation. What he says, the last thing there, the forecast should be informative for the user. This, I think, is very important as well. And so an example of that, if I were to now generate a temperature forecast for Cambridge for tomorrow, and I will tell you it's going to be between -10 and +40, I am probably going to be correct, and that is completely useless, right? So therefore, we have to have this informative aspect in our sort of evaluation as well. And then the first thing he says about the consistency between the judgment and the forecast, that sort of has to do with some sort of a decision theoretic principles that if I sort of somehow, if I know the true process of the thing that I'm predicting, it shouldn't be, my forecast shouldn't be evaluated in a way where I'm rewarded for saying something completely different, just because that is going to make me look like a better forecaster. So that is sort of this first thing there. And then a little bit later, Knighting, Balabdouai, and Raftery came along and says, we propose that we should evaluate probabilistic forecasts so we maximize the sharpness of the predicted distribution subject to calibration. Now, the sharpness thing here is the same as Murphy when he talks about that the forecast should be informative, right? The sharper the predictive distribution, less uncertainty, more information in this distribution. And then they say that we should sort of maximize this relative to calibration. Now, we have a whole workshop on calibration next week, so there's a lot of things that go in there. The basic idea is that if I predict that something is going to happen with an 80% probability, 80% of the time I issue that forecast, we should see that event happening. That's sort of what we can think about here. So under this condition, we then want to have as little uncertainty as possible. And then just sort of a little bit for our setting. So what we're assuming here is that we have some n random variables that we observe. They're identically distributed, come from some distribution G. We observe these n observations Y, the gray lines here, but the distribution that they come from the G is unknown, and this is what we want to predict. So I create my forecast F, which is this new distribution here. That is actually a forecast for the next observation yn plus 1, which is then this. And so then I somehow built this forecast F using the n observations, potentially some other external information that I think might be useful in my forecast. And so basically what I now want, I want some sort of a numerical measure that tells me whether this distribution here is a good forecast for this observation here. Now, the classic way to do this is to look at proper scoring rules. So I have some class of distributions, probabilistic forecasts, in this case on the real values. And then I say that a function s that takes in a distribution and a number, which is then y plus 1, and gives me a number, that this is a proper scoring rule if, in expectation, I optimize the score when I issue the true data distribution as the forecast. So this is the classic setting, and optimizing here means a lower value, so the score is a penalty. And then if there's a strictly sort of strictly smaller here, then we say it's a strictly proper scoring rule. If it can also be equal, then we just call it a proper scoring rule. Some examples here of some well-known, well-used proper scoring rules. If we take the just the negative log likelihood of my forecast and I plug in the observation, I get something that is called the logarithmic or the ignorance score, and that is often used. We also have widely used the continuous rank probability score, where I take my predictive distribution and then I build my observed distribution as the empirical distribution of this one observation that I have, and then I look at the squared difference between those two distributions. I can also look at some functionals. I can look at the mean functional and then I use the squared error, or I can look at the median functional and then I use the absolute error. And we can see that these two last ones, they're not strictly proper scoring rules because we're only evaluating the mean or the median. So all distributions that have the same mean will get the same expectation on that one. Now, this is sort of classic stuff. Thing to think about is that in reality, when we then apply these, they are sort of minimized in different parts of a distribution, and sort of the penalties, the shapes of the penalties are different. So here we have the distribution we're looking at is the GV distribution, so it's heavily skewed. The observation moves on the x-axis, and then we can see the score that is given to the observation for this forecast as a function of the observation. And we can see, for example, the squared error is minimized in the mean of the distribution, the absolute error and the CRPS in the median, and the logarithmic score in the mode. So asymptotically, everything works here. When we have small sample sizes and none of the models that we're actually evaluating is the true model, because that's usually what we have, we can have this issue that these proper scoring rules can give us different rankings of the models that we're comparing, right? And that happens just because there is a randomness in where the observations are relative to the forecast. And sort of important to remember is it doesn't necessarily mean anything is wrong with what we're doing. It's just we have a finite sample size, and so these are evaluating slightly different things. So now, if we then go to extremes, then here are two settings that are asking slightly different things about how good an extreme forecast is. So the first case is, I only care about extremes. So I built a forecasting model to predict extremes, and then I want to evaluate how good my forecast is at predicting these extremes. There's nothing sort of special about this first case. This is what we're usually doing. So the only thing that is special about this is that we have little data because we're looking at rare events. The second one is slightly different, and there we have to think a little bit more. So I issue a forecast for every type of outcome, for example, a weather forecast. And then I only care about how well this forecast does in those cases when an extreme was observed. Now this is, for example, the Met Office might need to do this because no one complains about the weather forecast when the weather is good and nothing special is going on, right? And so when there's a high-risk event, we really need to make sure that our model is doing a good job. And so here, then the question is sort of how do we do this? How do we take this general model that we use for every sort of outcome and evaluate it on a very small subset of the outcome space? Now, the most intuitive thing to do is to look at something like the restricted score. I take my favorite proper scoring rule. I put a little indicator function in front of it, and I say I only want to evaluate a forecast in case my observation is over this threshold t that I have chosen. So then I get this new scoring rule, this restricted score. Problem here is that if I have any function g that has a heavier tail than f on this part that I'm restricting the outcomes to, I will, in expectation, always get a lower score for the g than for the f, independent of what the true sampling density is, right? So this is quite common that this happens. But the obvious thing that we're missing here is that we're not accounting for the rate of occurrence. We're not accounting for the probability of occurrence of this extreme. So therefore, you need to normalize. Exactly. Because otherwise, if I just have a forecast that says everything is above this threshold all the time, that's going to be the forecast that does best under this. So basically, under the scoring rule, the best prediction is the one where we just move all the mass to be above the threshold, right? So therefore, exactly, solutions to this is that we need to normalize. And there's a couple of ways of doing that. Here, this was proposed 2011, so some years ago. This is nothing new here. We can take the logarithmic score and we can change that so that we restrict it to the part we're looking at and we also renormalize the densities. So we renormalize all the densities equally so that they all have the same mass on this part that we're interested in. And so this then now is a proper scoring rule because we've sort of built in this occurrence in a way. The other way to do that, which is to kind of do this correctly according to sort of decision theory, is what is here on the top. And this is that we take the CRPS, which normally would compare the full distributions, and now we put the weight function under the integral. But this is a different thing we're doing now because we're not restricting the outcome space, we're restricting the space of the part of the forecast that we're evaluating. So now I'm only evaluating, say if this is the standard sort of threshold indicator function, that means I'm only evaluating my forecast above the threshold independent of whether or not the observation was above this threshold or not. So these are sort of two different philosophies of how to correct for this. And we wrote a paper on this in 2017 where we talk about sort of different ways. And since then, there's been more work where people have looked into this a little bit. So that was still just a background. And then what I want to talk about a little bit more is this third setting here, which also has to do with evaluating extremes. So now I am issuing a probabilistic forecast for every type of outcome. And what I care about is a specific functional of that predictive distribution. So now I want to know whether or not I'm doing a good job of predicting a specific tail property or a functional of the true distribution of the data, not necessarily just the next data point. And so then we move the setting for, so I now still have this forecast F, and now I might be interested in that star over there. And so I want to know whether the red star and the black star match. And the information I have to compare these is that I have observed some new data. So I don't actually observe the black star, but that is the thing I'm trying to evaluate in reality. So the classic way to do this is that we now apply something that we call a scoring function rather than a scoring rule. So this now takes two real values. One of the values is the predicted functional. The other value is an outcome. And so I compare the predicted functional to an outcome. And then I get a positive number, which again, a lower number is a better score. And then we now need to have a match between the scoring function and the functional. So I can't apply any scoring function I want to any functional I want, because I need, in addition, that I'm optimizing the scoring function in the first variable, so that this functional is also the best functional I could have picked from the whole distribution when it's evaluated under the scoring function. And I say that if such a scoring function exists, then T is a elicitable functional. I can evaluate it in this way in the setting using a scoring function S that is consistent for it. And here are some examples. So the mean is elicitable. We've seen the scoring function before. That is the squared error is an example of that. For the median, it's elicitable. We can use the absolute error. Other functionals, for example, the mode is not elicitable, and the variance is not elicitable. And this Osband here, 1985, is a very interesting PhD thesis from the University of Berkeley that was never published in any papers. So one can go and read this nice thesis, and there's a lot of theory on scoring functions in there. And so basically, the problem with the variance is that you have to have sort of consistent level sets. So if you take a mixture of two distributions, then the functional of the mixture needs to be the mixture of the two functionals of the distributions you started with. And we don't have that for the variance, and that's why that's not elicitable. However, we can sometimes have that we can take two functionals, one which may be elicitable, one which may not be elicitable, and we can evaluate these jointly, even if we're not able to evaluate both of them separately. And an example of that is that the mean and the variance, we can evaluate these jointly. And here is an example of a proper scoring rule that evaluates these. If you look at this for a little bit, you may notice that this gives us equivalent rankings to the logarithmic score for the normal distribution. So basically, what this says is we can get a proper scoring rule by plugging the mean and the variance of the forecast into the logarithmic score for the normal distribution. And this is then strictly proper if the distribution, the class of distributions is such that we only need the first two moments to determine the distribution. If we have more information we need, this is no longer strictly proper. Some more, when we go into risk measures, we have that all the expectiles are elicitable, the value at risk and the quantiles are as well, but the expected shortfall, so the expected value, given that we're above a certain threshold, which is given by the value at risk or a given quantile, that is not elicitable, but we can evaluate that again jointly with the quantile we're using for the threshold. And then we're going to go into the quantiles a little bit more in detail. So a scoring function for quantiles is consistent if it is of this form here, where h can be any non-decreasing function. And what we usually, so the usual thing to use here is to use the identity function for h, and that will give us the pinball loss that is used in quantile regression. That in this case is called the quantile score. So basically what this does is that it looks at the difference between the quantile and the observation, and then that gets a weight which depends on the quantile, and it depends on whether or not we're above or below the quantile that we're predicting. And then we're going to look at an example just to see what happens here. So I have my ideal forecast, which is the true data distribution, is an exponential distribution where for each observation, I also draw a random parameter. So the parameter comes from the gamma distribution, and then I have these gray densities here, which you can barely see, which are two examples of this. And then we can integrate out the randomness in the parameter, and then we get a generalized Pareto distribution. That is the solid line here. So that means for every forecast outcome, I issue the same forecast. It's always the marginal distribution. And then I have the third competitor, which is an extremist, which knows the true parameter, knows it's an exponential, but divides the parameter by 2. And that is this dashed line here. So we see this thing here will always have a heavier tail than the true distribution. And then we want to compare a little simulation study where we simulate some data and then we evaluate that data based on for these three competing forecasts. So here's a visualization of what's going on. So we have, again, the density of the forecast is in gray here, which is very hard to see. this is the quantile that I'm interested in. This is the weight that I give to all the observations that fall on the left side of this quantile. And this is the penalty that I give to the observations that are above. And then we can do this for some different quantiles. We see that in all cases, the ideal forecast, which is the truth, is given the best score. That's good. Theory holds. But then when we then compare the marginal and the extremist, we see that for 0.9 and 0.95, the marginal forecast is getting a much better score. So that is now the second favorite after the truth. And then when we go even further out into the tail, this flips, right? And when we go way out into the tail here, it says that the extremist is better. So remember that we can't compare the numbers for the different columns. Those are not comparable because we're comparing kind of apples and oranges across the sort of across all the different columns. So we can only compare inside of a column.
So the aim is to get the smallest
Yes, small is better.
smaller.
So small is better. So for all three, the true distribution is the best, right? Now, normally we don't have the truth, so let's imagine that's not there. And I just have my two competing forecasts, and I need to decide which one of them to use, right? And we see that it depends on whether I'm in this part or I'm in this part of the table, right? So what is happening here is that when we go really far out into the tail, there is the extremist is predicting a quantile that is so high that no observations fall on this side, right? So therefore, all the observations are giving weight that looks like this, right? So what this is saying, in practice, what this means is that we can't actually evaluate our models for quantiles so high that we've never observed anything above this quantile, right? So it's basically, we can't evaluate that what we have not observed, right? And so that's kind of what's going on here. And so getting a result like this, that is just telling us that we kind of have to stop here because this is not valid. We're evaluating something we've never observed. So then, wait, I don't know what this is doing here. So now what we've been doing is we've been doing this procedure. So probabilistic forecast is issued for every type of outcome. We want to know how well a certain functional is doing in terms of predictive performance. And then we can reframe this as a probabilistic forecast is issued for an estimate of a functional of interest, and we want to know how good it is. So basically, we can transform our problem to evaluate a functional against observation to evaluate a functional against an estimate of that particular thing I'm trying to forecast, right? That puts a little bit of different constraints on the data that we have for our evaluation, because before we just needed one observation per forecast. And then we need a bunch of these, and we can take an average, and we have a number. Here, for every forecast, I need to observe enough data that I think belongs to this particular forecast so that I can actually estimate the functional I'm interested in, right? If it's a mean, I just need one, so it's fine. If it's a variance, I can't do that with just one, so I need more. And so, again, so we just saw on the previous slide that the variance functional is not elicitable. So I can't use this thing of consistent scoring functions to evaluate it. However, if I have repeated observations and I assume these to be IID, I can build the very standard empirical estimate of the variance. It's an unbiased estimator, and therefore I can evaluate the variance of my forecast against this estimator using the squared error, and this is going to be a proper evaluation of the variance, right? So now we've moved out of the standard setting, because in order to build this, we need at least 2 observations. Otherwise, we can't build this. Preferably more, but 2 is the minimum. And so, therefore, it is sort of outside of the consistent scoring function setting, and it works. But we also have a paper where we show that you don't have to have an unbiased estimate of the functional. You can actually do something like this with any estimate of any functional. It can be biased, but you then have to apply this biased estimator on both sides of the scoring function. So you have to apply it both to the forecast and you have to apply it to the observations. So basically assume we've observed now a vector of IID observations of some finite but random number, say n. And then, because I assume, so these are IID, then I can build a multivariate forecast where each margin is equal to my forecast f, and they are independent, right? So that is a multivariate forecast for this vector y. And then I can now build the push-forward distribution of f, this multivariate function f, under the estimator of the functional. And so then I have now a scoring function, a scoring rule that applies this estimator to both sides of this scoring rule. And then I have something that is proper if the function, the scoring rule that I start out with is proper. If I start out with a strictly proper scoring rule, it may not stay strictly proper, but it will at least be proper. And so, as an example here, we can use the continuous rank probability score, which we now call continuous ranked feature probability score. So there's one more letter in there. And this is a slightly different way of writing it. So basically, what we have here is we look at, this is the estimator of this functional under the observed data. This is the estimator of this functional under a random draw from my multivariate distribution. So I draw another random vector of the same size as the data, and then I estimate the functional, and then I take the expected value of this. And then I have another part here where now I have 2 random vectors from this multivariate distribution. I create the estimator for each of these, and then I look at the expected value of the absolute difference between those 2. So now I have a way of properly evaluate any functional that I want. It doesn't matter if it's elicitable or not. What I need is enough data to do this evaluation. And then in the end, I have a little case study where we're looking at an actual problem where we are now going to compare the quantile score, which is the standard way of doing this, with this new way of doing it, where we have this additional sort of estimation in there as well. So here is a valley in Norway, beautiful Norway. You can see there's a house in the river. So there's some flooding, which is something that unfortunately happens quite a lot, since we have a lot of rivers that tend to flood in the spring or in the fall. And if you are building, someone needs to build an infrastructure, whether it's a house or a road or a hospital or what it is, in a flood-prone area, then we have to look at what is called the design flood value, which is how large a flood do we expect at this particular location for a given annual exceedance probability. And these are sort of on the order of 0.05, 0.005, or 0.001. So small probabilities here. There's a law that tells you which of these probabilities you pick for which type of building. So you don't, if you want to build a garage next to your house, that is not the same rule or standards as if you want to build a hospital, right? And so in order to come up with these numbers, we need some data. So we can go to the nearest gauging station where we have observed some discharge. We can look at the annual maxima series for this particular location, which we have an example of here from 1950 to 2014. And then we can fit, say, a GV distribution to this data on the left-hand side. We can, for example, be Bayesian because we want to account for uncertainty. And then we get that, so here on the right, we get our results. So we have now plotted this sort of as a quantile plot. So we have the annual non-exceedance probabilities here. And then we have those black dots are the data points, and the dashed lines are the uncertainty bands I get from my Bayesian inference. Right? So now the person that needs an estimate here is the dam owner. And they need to know whether or not their dam is high enough to withstand the water that comes to this dam. So they need the value that is associated with this annual exceedance probability over here. So that means I have that nice interval over there, and they need to pick a number inside of this interval because interval is not good enough for them. They need a fixed number, right? Because the dam has a fixed height.
I didn't see the interval.
Yes, it's very light gray. Do you see it now?
Yeah, I do.
Good.
I thought you were thinking about the whole interval and the big one was in him out.
Oh, that's a lot.
Yes.
Yes. And so here are now 3 different ways in which we can use a model to come up with a number out there on the very right. I can do the classic Bayesian thing. I take the posterior predictive distribution, and then I just look at the quantile of the posterior predictive distribution that corresponds to this value. That's the blue line there. Another thing that is also commonly done is that we take the likelihood, in this case the GEV, and then we take one set of parameters, for example, the mean posterior parameters. I pluck these into the likelihood, and then I have a distribution, and again I can calculate a quantile from that distribution. That is the red line. And then a gray line, which is almost equal to the red line in this case, is sort of a robust estimate, where I take all the quantile curves from all the quantile curves I get from my MCMC, and I pick the median of these curves. I can either look at only this particular probability here, so then I just have numbers and I can pick the median number. If I want a consistent curve, I can use sort of functional band depth to pick the median curve among the curves. So now the problem that we have is that these give us different numbers, but where we have data, they're identical, right? So then how do we pick which one of these is the best? And this is a practical problem we came across a lot when we were doing this. Which one to pick will depend on which side of the table you're sitting. The dam owner will tell you, I want the lowest number, thank you. The regulator will tell you, well, give me the highest. We want to be sure we're doing this right. Right? And there can be a lot of money in between those two numbers. So then what we do then is we try to do this sort of, okay, let's go back. So then we try to do a systematic analysis of this using some data. So I pick out 12 series from around Norway where I have a really long series. And then I take out 60 of the annual maxima. I pull those aside. I estimate the distribution based on the remaining data, which is usually 50 data points or more. And then I fit with the data points I have, and then I try to estimate that those quantiles I'm interested in based on the data I've left out. And then I reshuffle and I repeat this many times. And so if we do that, we can estimate sort of events related to exceedance probabilities like 0.02 or 0.05. That's about as far out into the tail as we can go when we're interested in, when we have 60 data points to use for the evaluation. And then we compare now these three distributions you just saw on the previous slide with the quintile score or this continuous rank feature probability score. So we have then in total 300 forecast instances. So these numbers here are averages over 300 results, basically. Each of these is based on 60 data points. So for the quintile score, I have 300 times 60. So I have 18,000 numbers that go into the average quintile score here. And what we see is that the worst model is the one on top. So the posterior predictive distribution gets the worst results. There are other studies that also have shown that there tends to be a positive bias in the posterior predictive distribution when you go really far out into the tail. There is even some very nice theoretical results that show this that were not published because the reviewers didn't like negative results. And at some point the authors gave up, but which I think is a shame. Yeah.
So I imagine it depends on the prior.
Yes. So it does depend on the prior, but so all of these come from the same MCMC.
Yeah.
So of course, if I put very, very informative prior, that kind of force everything to not blow up. And that has to do if I put very informative prior on the shape parameter, I can basically do something where I force the blue curve to be more or less where the others are. So now, of course, here, because I'm trying to get some separation, I am trying to not kind of, I try to kind of be non-informative. Yes. Yes.
So I'm just trying to understand. So in your scores, isn't it related to the absolute value in the sense of somehow the L1 norm?
Yes.
So the posterior mean is associated to the L2 norm. So it's like so somehow you had chosen a score associated to the L2 norm. Maybe you would have the posterior mean, which is a Bayesian version. But because you use the L1 norm, then you go for the median. Is there something like that going on, or is the thing something else?
So yes. So I think yes and no. So these here. So here you have GV. So there's a lot of decisions here, right? So here I'm choosing here the posterior parameters. I have the posterior distribution of the parameters. I'm picking some value. Here I could have taken the mean or the median, but then I'm convoluting that through the likelihood.
Yeah, yes.
And then this one here, I am picking the posterior median, which is robust. And then I'm using the CRPS, which is the absolute error if your forecast has no variability, if it's a point forecast, right? Because it's Exactly. So if your forecast is just a point mass, then this part here falls out because there is no variability in the distribution. And then what you're left with is this, which the expectation also falls out because it's a point mass. So then you just have the absolute error.
Yeah, but I wanted to say that so the posterior predictive, it's a posterior mean. So it's a posterior mean of the density.
Yes.
And so it's the minimizer of the L2 norm associated to the posterior risk associated to the L2 norm.
Yes.
So I was wondering whether we're here, looking a bit at something which is more like to the L1 norm, in which case the posterior median would be left first.
Yes.
In terms of the density, not of the parameters, but of the density.
Of the density.
So maybe this is what you're seeing, or
this is exactly what I'm seeing, right? Yeah. Exactly, because this here is sort of this median posterior quantile curve here is I am actually looking at all the quantile curves and I'm picking the median of that distribution, which, like you say, whereas this one here is picking out the mean of that distribution.
So had you chosen like the L2 sort of scoring rules, some kind of square rule, then maybe you have chosen the other one.
Exactly. Yeah. So it also depends on the scoring rule. So that's a very good point. We should add a third column here because that's also a proper scoring rule. Yes. Yeah. Thank you. Yes.
I'm sorry, but there is no confidence interval. The score tends to be relatively close. So
yes.
Because it's everything is empirical.
Everything here is empirical. What we can do is yeah, so I mean, how do I say whether those are two different numbers or really the same number? Right? Those are two very small numbers. So in this case, because we're kind of doing a simulation study where each is like there's high independence between the individual forecast cases, we can do bootstrapping, right? And so we did bootstrapping, and all of these are significant under bootstrapping. Alternatively, there are tests one can do. There's something called the Diebold-Mariano test, which is sort of like a t-test, which just sort of looks at whether these are really different, and then you have to estimate the variance of these individual things. You can also do a permutation test, which then tests the full distribution of the scores. And so yes, that is true. We have done sort of the bootstrap analysis of all of this. Everything here is significant, even if these numbers are very small. Yeah. And there's a larger variability between these, but these are also averages of fewer cases, so there's a slightly larger variability, but these are also significant. And then if we then go to a simulation study, we can we're not restricted to basically how many data I have. So basically, what the law tells me I need to do if I want to build a hospital or if I want to build a dam, even if I have over 100 years of data in many locations, I have no way of properly evaluating any model for doing this, right? We have to use simulations, right? So it's sort of in this setting, 100 years of data is not very much because we're going so far into the tail. But here we did a simulation study. So where we, what I do is I take a GV distribution with some parameters, I simulate 100 data points, then I estimate the station MCMC using these 100 data points. I built my competing forecasts, and then each of these forecasts is then evaluated with new 100,000 simulations from the true density. Right, so now I have 100,000 years of data that I use to evaluate my model, so I can go a little further out into the tail. And then I repeat this 600 times so that for the quantile scores here, I'm really looking at numbers that are averages over 60 million data points. And so what we see here is that the true data distribution now gets a much better score than everything else. That's good. So the theory holds. but we see that for the other models, we are still observing exactly the same rankings. And here, again, even these numbers here are significantly different just because I'm using so much data. So at least under this setting where we're using sort of a fairly robust score to evaluate this, it seems that we are doing well in sort of using a robust estimator of this. And in practice, the problem here is that so basically, there's a law that tells us what we need to estimate. Then there are guidelines that describe how to do the estimation. And then there's a consultant who does the estimation. They have about 3 hours to do that. And then their estimations are sent to the regulatory body, which checks their calculations and says this is good or this is not good. One of the important things is to actually propose robust things so that there aren't occasional things where things blow up and no one noticed, right? Because that sort of might happen. And that is actually something we found a little bit with the posterior predictive distribution, is that you can have cases where the thing blows up and it sort of wasn't noticed. And then all of a sudden you have to spend 500 million kroner rebuilding your dam. So it is sort of robustness is a thing that we kind of care about here. And then we can also try to compare those two things, the quantile score and this feature probability score, in terms of sort of how good are these at discriminating the methods, actually. And so what we do here, we do the same thing. I simulate 100 data points from some distribution. I do my Bayesian and CMC. I build my forecasts. And then I change sort of how many data points did I use for the evaluation of this forecast. So for each case, so I start with like 1500. And this is the I think this is the exceedance probability of 0.001. So there's very few data here that are very large. And then I go up to about 100,000 for each instance. So here I really have observed something. And then I repeat this many times. So I can then look at the fraction of correct ranking. So that means I compare the true data distribution against a competitor, which is not the truth, and I count the fraction, how often was the true distribution picked as the better of these two, right? And then I have 3 different lines for each evaluation because there are 3 competing forecasts which are not the truth, right? And then the scores say that the posterior predictive distribution was the worst of the 3, and therefore the fraction of correct ranking is highest for that model. So the model that overall gets the highest score, so we said this is the worst model, it's also easiest to correctly identify the truth against that one. So the relative sort of, if we look at, say, your 3 black lines here, there's the dotted, the dashed, and the solid. And this says that it was easiest to correctly identify the truth against the model that on the previous slide was assessed as the worst, essentially. But then for each type of line, there's a gray line, which you can't really see, and a black line. And the black line is if we do this under the quantile score, which is the consistent scoring function. And the gray line is if we do this under the CRFPS, where we estimate the quantile using the data and then evaluate that estimate. And what we see is, of course, if we're out here, sort of, we have enough information. Doesn't matter what we do, we're good, right? We are never here. So let's see what happens sort of down here somewhere. We're never really here either, but let's imagine. And what we can see is that, of course, using the quantile score, where we don't have to do this additional estimation step, it is a little more efficient than the other one where we have to do this estimation step. So we sort of expect this to happen. But we can now, there's not a huge difference in the efficiency, and we can evaluate, we can apply this new thing here for any functional, not just functionals, for which we have consistent scoring function. Yes.
So it feels like, maybe I'm just misreading, but it feels like at the very beginning of the curve and at the end there isn't much difference, and there is more difference in the middle. So I was wondering whether like it's some kind of artificial fact of the 13, or like at 1.5 it seems to be like almost the same for everyone, and then it grows the difference.
Yes, it's because it is has a reason. Because for the lowest one, we're always on this side, and we're never on this. Yeah, so it's basically the evaluation procedure is kind of failing, because we essentially don't have enough data to evaluate what we're trying to evaluate.
So it's not really just the evaluation system.
Exactly. So it's kind of just showing us what we're seeing here again. Yeah. Yes, I think I just have my summary, and then we're good. So yes. So to summarize, we have these nice decision theoretic principles that tells us how to do things. It's important to adhere to these principles when we do things. It is also important to remember that we are never working in the asymptotic case. So when we're only comparing wrong models, we can get something that doesn't look quite right, and that's just because we're dealing with data. So basically, we can't perform predictive evaluation of things which we haven't observed. Just like we can't evaluate our models, we can't do inference on something that we haven't observed. So this is exactly the same thing. For functionals, if we have good enough data, we can overcome this lack of elicitability by basically transforming the observation from the outcome space to a different space where we're looking at functional estimators. And that was it. Thank you very much.
Thank you, great talk, and the question for me.
And you want to go ahead, I've already asked you.
So you take, 100 years of data isn't really a lot, but we've got a changing climate and so on. So it's not, so we've kind of got a unique, how does the scoring rule kind of framework work when you know you're in a changing environment?
That was my question to you.
Yes. So so basically, when we're in a changing, because we are like, so what we did here, which is sort of the standard thing, is that we assume that our series is stationary, right? Yeah. Which is not true, right? So I will just show you the example. So this one here starts, I start plotting here in 1950. Actually, it goes back to 1896, but it looks more or less stationary. Then we had this large flood here in 2014. Since then, we've had 4 more that are of that size. So yes, and so then basically what we need to do is that we need to build into our GV distribution non-stationary components, and then really we sort of only ever have one observation for each forecast, because the forecast is changing from year to year. What people do today is they fit the stationary model, and then someone else has done like an independent analysis which says, like, if you're in this part of the country, the effect of climate change is 30%. So you get a number and then you put a 30% on that number. If you're in a different part of the country, it's 40% you put on top of your number. So it's a little ad hoc, but yeah, it is. It's a little tough. The non-stationarity is a huge issue. and it's kind of hard to actually model it well.
So I like a general story question about which feeds into this. I mean, so I'm confused about what I should do in life, right? So pretend I'm a good Bayesian.
Right.
So I elicit my best prior, my best model, and then I report my true belief.
Right.
What should I? So that's my forecast as a forecaster. And now you come along and evaluate it. What should I do as a forecaster, given that knowledge?
Yes. So there, you need to ask me, how are you going to evaluate my forecast, right? And then I tell you, this is the evaluation function. And then you need to basically be a proper Bayesian, and you need to minimize, you need to calculate the minimum expectancy and your penalty given for my evaluation rule, basically.
We change my cost function essentially to be your score.
Yes.
Yeah.
So if I'm using the squared error, you want to pick a mean.
Yeah.
And if I'm using the absolute error, you want to pick the median.
Mm-hmm.
So we need to talk before you decide what to do, basically. Yes.
Yeah, I had the same question. So
Yes.
like with the non-stationary function.
Yeah. Good.
Thank you again.
Yes, thank you.